Hi, everybody. This is chapter 9, optics, and the topics we'll be covering in this chapter are light waves, reflection, diffraction, interference, both constructive and destructive. We covered this a bit in chapter 6 with sound, but now we'll cover this with light. Polarization, one-way mirrors, refraction, total internal reflection, which includes touch on the critical angle, lenses, magnification, eye surgery, and how that helps people that are nearsighted, color, and blue skies. So let's go ahead and begin. All right, section 9.1, light waves. And we discussed this in chapter 8, but light waves, light is actually the entire electromagnetic waves bandwidth. But in common everyday parlance, light generally refers to this narrow band of electromagnetic waves that human beings can perceive with their eyes. All right. And so it's got frequencies F from about 4 times 10 to the 14th hertz. It's a very narrow band, 7.5 times 10 to the 14th hertz. So you see, it covers even less than 1 order of magnitude. And if you recall, when we were discussing the other bandwidths of E&M waves, they covered several orders of magnitude, most of them, and a few of them covered more than several. So yeah, light waves, this visible light bandwidth is a very small bandwidth, all right? The wavelengths, and remember how we discussed that, C equals F lambda, with C being 3 times 10 to the 8th meters per second. And then if I put that in for F, lambda is going to have a range from about 1 nanometer. So yeah, just about one. It's going to be in the 10 to the 9th, negative 9th range. That's what the wavelengths. Very small, very, very small. All right. So these wavelengths are really short. All right. Reflection. It's a very, very extremely common. Most everything we see, light is reflected into our eyes. Unless we're staring at a source of light, a fire, the sun, light bulbs, something that actually produces anything glowing. If I'm staring at anything in the room, it's going to be reflecting light. Okay? So, reflection is very common, and the law of reflection states that the angle of incidence equals the angle of reflection. And what do I mean by that? Well, let's pretend we have a mirror here, and let's discuss what those mean. The normal is a term that everybody should know. That is a line that goes perpendicular to the surface. So on this side, I have a 90-degree angle, and on that side, I have 90-degree angle, right? A normal is always perpendicular to the surface. Okay, if I have a light ray, incoming light ray here, outgoing light ray there, these are supposed to theta and theta. They're supposed to be equal. My drawing skills are not that great. So this is incoming, that's outgoing. The incoming is called the angle of incidence. The outgoing is called the angle of reflection. And so the law of reflection states that the angle of incidence equals the angle of reflection. Okay, two types of reflection. Specular reflection, the familiar type we see in a mirror or in the surface of a calm pool of water. It's very smooth. So reflection occurs when the direction the light wave is traveling changes. Diffuse reflection occurs when light strikes a surface that is not smooth and polished, but uneven, like the bottom of an aluminum pan or the surface of paper. The light rays reflect off the random bumps and nicks in the surface and scatter in all directions. Diffraction. We talked about diffraction in chapter 6, but to refresh your memory, as with all waves, diffraction of light as it passes through a hole or a slit is observable only when the width of that opening is not too much larger than the wavelength of the light. Okay, so we talked about this in chapter 8, but remember we spoke how you can hear voices when you're walking down a hotel or an apartment hallway, but you can't see the people in there. That's because light waves are much smaller than sound waves, and sound waves diffract after they pass through the opening. So what happens is waves that have a similar wavelength, this would be a wavelength, they come out and they diffract. They spread out as they go through the opening. Let's say that's a doorway. Okay. And that's diffraction. So the narrower the slit, the more the light spreads out. We also talked about interference of sound, but we're going to talk about it with light. It occurs with light as well. So waves undergo interference. When two identical waves arrive at the same place at the same time, they add together. If the two waves are in phase, in other words, if the waves are in phase, something like this, the peaks and troughs are in sync, if you will, the resulting amplitude is doubled. It's called constructive interference. Now, if they're out of phase, something like this, that they cancel each other, and this is called destructive interference. So this phenomenon was used to prove that light was actually a wave. When light passes through two narrow slits that are close together, the two waves emerging from the slits diffract outward and overlap. So something like this. If the light consists of a single frequency, you can place a screen behind it right here, and you're going to get bright, let's say those are bright and dark alternating images. Okay, where the two light waves overlap, and they're in constructive interference, you'll have those bright spots. The dark spots are the result of destructive interference. So this was used by Young when he did his famous experiment. And this proved definitively for the first time that light was in it a wave. It had wave-like properties. And this was a hallmark experiment in the science of physics. Young's double slit experiment. And if you go on to take more physics in your career, you will no doubt be doing this experiment. It's a very popular one to do in physics labs. So Young's double slit experiment proved definitively that light had wave-like properties. All right, so we've already proved light was a wave, and now we're going to talk about polarization because that proves it is a transverse wave, not a longitudinal wave like sound. So transverse wave means that it's like this and not like the bunching up waves of sound. All right. Okay, so let's see. Light can be polarized. So a Polaroid filter, like the Polaroid sunglasses, absorbs light passing through it unless the light is moving in a particular direction. So as light strikes your sunglasses, some is like this, some is like this, some may be like this. So your sunglasses only let light going a particular direction pass through. This eliminates most of the glare, okay? Glare is caused from the random light direction, all right? So your sunglasses absorb all the random direction. All right, one-way mirrors. They've got them in police stations, in casinos. But what are they? A one-way mirror is made by partially coating glass so that some of the light reflects and some of it passes through. It's often called a half-silvered mirror because it's not opaquely coated. So when used as a window or a wall between two rooms, it will function as what we call a one-way mirror. If one of the rooms is bright and the other is dim, it'll appear to be an ordinary mirror in the bright room because all that light will reflect back. But in the dim room, you'll be able to see through it. So you don't want to be on the bright side of a one-way mirror if you can avoid it, because that means people will be watching you. Anyway, so a person in the dim room can see what's happening in the bright room without being seen by anyone in the bright room. All right. So it's it's in interrogation rooms and in casinos. So this is called a one-way or a half-silvered mirror, and you don't want to be on the bright side of those if you don't like people watching you. All right, refraction. Okay, so light has this interesting property that we exploit to make eyeglasses and telescopes, etc. And it's called refraction. So what does this mean? So let's say we have some kind of boundary between two transparent materials such as air and glass. And here's our normal. And let's say we have a ray of light that strikes that boundary at some kind of angle, an incident ray that at some kind of angle theta, called theta incident, with respect to the normal. So we have an incoming light ray from air striking our boundary. Here's the normal. At some kind of incident light ray angle with respect to the normal. Well, what happens if our secondary material, this is our boundary, is more dense than the first primary material, our light ray will slow down when it encounters this denser material. And in doing so, it's going to bend towards the normal. We'll call this theta refracted. It's going to appear to your eye here, to be going straight through. That's why when you go fishing, the fish may look like he's closer than he really is. You have to make a little compensation for that. But it will actually slow down, and in doing so, bend towards the normal. And the amount of bending it does is a property of the materials. And this property of each material is called the index of refraction. And its symbol is a small case n. So this whole phenomenon is related by the n of the incident material divided by the index of refraction of the refracted material equals sine of the refracted angle divided by sine of the incident angle. Also, the wavelength of that light in the refracted material divided by the wavelength of that light in the incident. And finally, the speed of light in the refracted material divided by the speed of light in the incident. Because as I've already mentioned, the reason why it bends towards the normal is because it slows down when it encounters the denser material. So a couple values, n of air or a vacuum is equal to 1. And that's a nice thing to memorize. And also the V of air or a vacuum equals C equals 3 times 10 to the 8th meters per second. I know we've talked about that before, but that's also a great value to memorize. So let's do a sample problem. Let's say we have a angle incident that's in air, strikes glass where n equals 1.5. And note that this is a unitless quantity, has no units. All right, so n is equal to 1.5. And let's determine the velocity of that light in the glass. And how about also, we'll make up an angle. We'll say this is 32 degrees. And we'll determine that refracted angle. So we've got 1 over 1.5 n incident divided by n refraction equals sine theta refracted over sine theta incident. And that also equals velocity of the refracted over velocity of the incident, or C, equals VR over C. Okay. So I'm going to solve for this first one. Cross multiply and divide. So sine theta incident equals sine 32, sorry, 32. Sine 32 times 1 equals sine theta refracted times 1.5. I'll just go ahead and solve that. So sine theta refracted equals (0.353). So theta refracted equals sine inverse of 0.353. So I get 20.67. So theta refracted, 20.67. All right, that's theta refracted. Let me get some board space here. Now to determine the velocity. Okay, 1 divided by 1.5 equals V refracted over 3 times 10 to the 8th meters per second. So 3 times 10 to the 8th meters per second divided by 1.5 equals V refracted. And that's going to give us V refracted equals 2 times 10 to the 8th meters per second. And that's refraction. That's a good thing to study. You're going to have a lab like that. So I suggest you study this, and it'll help you much with your lab. Anyway, this property of light, this wonderful property of light, we exploit to create lenses. And we're going to talk about three very simple cases, 3 simple cases. Convex lenses. So let's talk about the first case. So we have a lens here. It's curved, it's symmetric, and it's curved on both sides. And you might have to use your imagination to see that. But these, the amount of curving is called the radius of curvature. And so what happens is when light strikes this lens, it's going to converge to what's called the focal point. All these lenses have what's called a focal point. And if they're symmetric, the focal point is the same distance from the center of the lens on each side. All right. And so how does this work? So we have incoming light rays. When they strike the surface, they bend towards the normal, and they all converge at the focal point here, if they're all incoming parallel. But you may ask, well, what is the normal on a curved surface? Well, in order to find the normal, what you do is you take a line and you touch one part of the curve. So right at that point, the normal is going to be like that. Here, the normal will be like that. Here, there, here, the normal will be there, and so on and so forth. So the normal are really different along the curve. Therefore, every time a incoming parallel light ray hits it, they bend to a different degree, and they all converge at the normal. Now, if we have a flat surface, you see that then they're not going to, if the incoming light rays, obviously, if they are along the normal, they're not going to bend towards the normal, so they'll just go straight through, right? They'll never converge on a flat. And if you're just slightly curved, then your normals are not going to be so extreme, right? There's a very highly curved with a lens with a high radius of curvature. So what happens is your focal point tends to be farther away. It's closer when you have a high radius of curvature. It's farther when you have a flatter or a less extreme radius of curvature for these lenses. So that's going to be important to remember when we talk about eye surgery. But anyway, let's get back. I digress. Let's get back to the topic at hand. All right, lenses. Case 1. Incoming light rays are from the sources at an infinite distance are from a source held at an infinite distance and incoming light rays are parallel. Well, obviously the source is not at an infinite distance, but the source is going to be far enough away so that all the incoming light rays are parallel. So if we have Johnny here and light rays are going off in all directions, and if my lens is far enough, I will have missed all these light rays that go in weird directions. And the only ones I'll get are the ones striking parallel, because the ones that go off, obviously light is going to be reflected in every direction from Johnny. But the only way, if I'm far enough away, I'll only see those coming directly parallel. In other words, I can't see the top of Johnny's head or the back of his head or anywhere behind his ears. I'll only see these coming in parallel. So that's what that means. That's what an infinite source means in this context. So let's go ahead and talk about this. So case one, incoming light rays are parallel. So here's our lens, here's our normals. Our incoming light rays are parallel. And what happens in this case is your image is formed at the focal point. So that's case one. Case one, you've got parallel incoming light rays, and you have your image will be formed at the focal point. All right. All right, case two. Your object is held at a finite distance. However, it's outside of the focal length. Now your image will be real and inverted. What do I mean by that? All right, you could probably find better ray diagrams online, but I'm going to give you the best I got here. Here's your focal point. And now these are typically done like this. You got three rays. You got one coming parallel, one going through the center, and one going through the focal point. The one going through the center just keeps on going through. The one going through the focal parallel goes through the focal point, and the one going through the focal point comes out straight. So here's your image. It's going to be inverted here. This is case two. Oh. And no doubt you can find a much better ray diagram online. So please, I urge you to do that. Case three. Object is held at a finite distance. And it's inside of the focal length. And in this case, your image is virtual and upright. So we have here, once again, our lens, focal point out here, focal point here. Johnny again, we got one coming straight in, one going through the center. And these will never converge on this side. So what you need to do is you need to take a mirror or some kind of other reflective surface and put it back through. Oops. And then if you have your screen on this side, you'll get a image here, but it has to be reflected back. So you don't get an image on the other side of the lens. It's a virtual. And then once you reflect it back, it will be large and upright. So those are our three cases. And I would love to urge you to go online and check out their very nice ray diagrams that they have there. Total internal reflection. Okay. Rays of light, consider now the following experiment shown in figure 935. Rays of light originating in the glass strike the boundary separating it from the surrounding air at ever increasing angles. So we're increasing our incident angle. In this case, since the speed of light in glass is smaller than the speed of light in air, we see that the ray is bent away from the normal, right? It only bends towards the normal when it slows down. When it goes from a more dense to a less dense, it bends away from the normal. Now, because, all right, the angle of refraction is going to be larger than the angle of incidence when it goes from a more dense to a less dense substance. Okay, now, because of this reversibility, we can use the same graph to find the angle of refraction where the angle of incidence is known, okay? So what happens if none of the light passes through? None of the light passes through, and we have a 90-degree reflective angle. This is called the critical angle. So here we've got this, and instead of, all right, here's our normal. So instead of bending towards, remember it's bending away. But if we can get it at such an extreme angle that it bends here, this is called our critical angle. And that occurs when sine theta refracted equals 1, or theta refracted equals 90, okay? All right, and so with that in mind, let's go ahead and do example 9.2, which states, a homeowner wishes to mount a floodlight on the wall of a swimming pool underwater so as to provide the maximum illumination of the surface of the pool for use at night. At what angle with respect to the wall should it be pointed? Okay, so here we only have to look it up. The critical angle for water is about 49 degrees. But we could say N incident divided by N refracted equals sine theta refracted, right, divided by sine theta incident. And if we had, this is going to be 1 because it's air, and this is going to be 1, right? So N1 equals sine theta incident. So we would solve it just like that. Or you can look it up in table 9.1, which gives you the critical angle of many materials. Either way. All right, now getting back to our lens cases, our 3 lens cases. Suppose we want to know where that image was formed, say case 2. All right, we have what's called the lens equation. Which says 1 over F equals 1 over S, and S is the object distance. And P is the image distance. Plus 1 over P. Now let's say I have F is 5 centimeters, so 1 over, and I wanted to figure out, and let's say I hold S at 10 centimeters and F is 5 centimeters, and I want to solve this. Well, what's easiest to do is to go ahead and not work with our values in the denominator. So let's get a common denominator on this side. 1 over F equals P over SP plus S over SP. And now I'll go ahead and combine these two. So 1 over F equals P plus S over SP. And now just flip them all. F equals SP over P plus S. And let's say I wanted to find the focal length, and I knew my object distance and my image distance. And so my object distance, S, is 5 centimeters, and my image distance, P, let's say 7 centimeters. So F is going to equal 5 centimeters times 7 centimeters divided by 5 centimeters plus 7 centimeters. And in this case, I've got 5 times 7 divided by 9, right? That's going to give me F equals 3.88 centimeters. So, and that's called the lens equation, and that's how you solve for your focal length with case 2. Okay, let's talk about eye surgery. Okay, if you care to check this out in your book, it's got a very, very nice diagrams. And so figure 6.9 shows a simplified cross-section of the human eye. Now, light enters the eye and is projected onto the retina at the rear of the eyeball. So what happens when we can see close up, but we can't see far? We can, what happens then is that is called nearsightedness, right? The light rays from a distant object are brought into focus before they reach the retina. So maybe your eye is too elongated. So when what happens is that it's remedied by flattening out the lens, actually. Remember we talked about those thin lenses have a longer focal length. So you flatten out the lens and you extend your focal length, and you correct it that way with eye surgery. Farsightedness is the opposite. Your eye is too short. And so unfortunately, flattening out the lens doesn't do the same thing. It only makes it worse. Finally, we want to discuss our blue skies. Why are our skies blue? Simply that more blue light is scattered in the sky than any other color, right? It's because of the air molecules scattering the sunlight. So as waves travel through the atmosphere, the waves oscillate electric fields, causing the electrons in the air molecules to oscillate with that same frequency. All right? So the emitted light, which travels outward in all directions, is what we see. Shorter wavelengths are scattered, the E scattering, energy scattering divided by time equals 1 over lambda to the 4th. As this gets smaller, this value gets bigger. So our shorter wavelengths are scattered much more than our longer wavelengths, like red. Red is a longer wavelength than blue, right? As the denominator of a fraction gets larger or smaller, I'm sorry, then the entire value gets larger. So the shorter wavelengths like blue are scattered much more than the red. So our book gives you the example. The wavelength of blue light is about 0.7 times that of red light. Consequently, there is 1 over 0.7 to the 4th times more blue light scattered as there is red light, and that's about 4.2 times. All right. And that concludes the summary for chapter 9.